Got it. One of the best things about being a moderator in a webinar is that I get to ask questions whenever I want to. So, so that's great. I had so many questions I remember, and I couldn't even fit them all in. So this is chance two for me. Yeah.
Yeah, happy to answer whatever I can.
Great. Okay, I'm gonna go to YouTube and then mute myself on YouTube. Just gonna type a welcome message in the YouTube chat, and then we'll get started. Welcome to the web. Okay, maybe we'll get started in about a minute, and then we'll let the audience trickle in. Okay, Abigail, are you ready to go? I might start in 10 seconds.
Yep, I'm all good to go.
Okay, great. So welcome everyone to the IBIPSA Research Committee webinar. My name is Gokul Paranjoti. Happy Thursday, and if you have any doggos, give them some extra pets from me. Today, we're going to learn about modeling enclosure-related applications for historical buildings by Abigail Sefa from Simpson, Gumpertz, and Heger. I will introduce Abigail in a bit, but before that, this webinar is hosted by the IBIPSA USA Research Committee with the goal to share new ideas from research to the building simulation community. Abigail is a project consultant at Simpson, Gumpertz and Heger in Boston. She received her SB in Architecture Studies and her Master's in Civil and Environmental Engineering from MIT. Her research at MIT focused on a variety of topics at the intersection between architecture and civil engineering, including analysis of structural tile systems, the use of CFD to trace particle spread in naturally ventilated hospitals, and construction techniques for reinforced concrete beams. Her work at SGH encompasses a variety of enclosure-related projects, including energy modeling, building enclosure commissioning, design of existing building renovations, computational analysis of existing and proposed building enclosure systems, and building enclosure consulting. AIA Continuing Education Credit is available for attending this webinar. Please email info@aiaeb.org with your AIA membership number to receive credit for attending today's event. I will also paste that email in the chat so you guys can refer to it later. How we're going to do questions, if you have any questions during the webinar, either type them in the chat window, but I would prefer that you type them in the Q&A option, and then we can have Abigail get to them and answer them at the end of the presentation. So I will mute myself and hand it over to Abigail.
All right, thanks Gokul for that introduction. Thanks for having me here. I'm going to just share screen. And get started. All right, today, as Gokul mentioned, I'll be presenting an overview of different ways that we can use building energy modeling, specifically in enclosure-related applications when it comes to historic building renovations. And this is kind of in the middle of the two worlds that I specialize in. I focus on building science and modeling work when it comes to our enclosure consulting at SGH. And then I also work on projects where we're doing historic preservation. So this is in the middle of those worlds. As Gokul mentioned, it's registered with the AIA. And before we get started, I'd like to learn a little bit about my audience today. I'm curious how many of you have experience with running building performance simulations. And this is more of a question of whether you personally have run a building performance simulation. It's fine if you have no experience, but I'm just curious who's in the audience today. All right. Great.
Abigail,
Okay, so
I'm going to give them,
yeah.
I'm going to give 10 more seconds for them to respond,
Okay.
and then I'll end it. Yeah.
Okay, sounds good. Seems like we have a pretty experienced group here today. All right, and one more question before we get started. Have you ever worked on a historic building renovation project? So that's the other side of this presentation. All right, so we have people who are experienced modelers, but maybe a little bit newer or unfamiliar with historic building preservation. Great to know, thanks. Okay, the goal is that by the end of the presentation today, you'll be able to understand potential building enclosure-related issues when it comes to building renovations. There are a lot of software programs out there, but by the end of this presentation, we'll be able to explain how specific software programs can help to evaluate the risks associated with modifying a building enclosure, a historic building. You'll be able to select which of those software programs should be used to evaluate the risk of a specific issue, and you'll understand some of the non-technical factors involved in historic building renovations, and those kind of set them apart from new design projects. I'd like to thank some of my colleagues at SGH for their help with this presentation. Those are Ned Lyon, Cheryl Saldana, and Maria Ragusis. Today's presentation will be guided by this building enclosure analysis matrix. The idea is that we have clients come to us with all sorts of renovation proposals for historic buildings. Sometimes they're proposing installing a new cooling system or creating a new high humidity space. Sometimes they want to install insulation, usually to improve the thermal performance of the building. And sometimes they want to install new windows and doors. Each of those interventions on the enclosure can have several negative effects on the performance of the existing enclosure and of the new assembly. Those include condensation formation, associated freeze-thaw cycles, mold growth, condensation on windows and doors, and they can also have an energy cost impact. So before, we generally want to do this analysis in the early stages of design. And when we're in those early stages, you'll need some information from your client, and you'll need to select a software with which to run different models to evaluate different risks. This matrix also includes some potential solutions and potential complications. The software tools that I'll be mentioning today are Lawrence Berkeley National Labs Therm and Window, Fraunhofer's WFI, the US Department of Energy's Energy Plus, and Design Builder. So here's another poll question for you all. I'm curious which of these software tools you have either used or heard of. So which of these have you heard their names around in the industry? Um, can you get the poll started, Gokul? There we go, thanks. I'll give you 15 seconds to fill that out. Okay, very interesting. I'm surprised. We have a lot of people who've heard of Design Builder. And of course, Therm windows are kind of staples in the industry. Okay, today I'll be moving through 4 different case studies. Our first is a client came to us proposing installing insulation on the inboard side of the historic masonry facade. This building was constructed in 1901 up in Vermont. It's a multi-wide masonry building, so there are 3 to 5 wides of brick, and then on the outboard side there's a wide of marble. You can see here in green. It's about 1.5 inch layer of marble veneer on the outboard side, and then on the inside we have an airspace and then a gypsum plaster and lath interior finish. And the architect was proposing installing spray foam insulation inside of this existing assembly, and also a new layer of interior gypsum board. If we look at our matrix, we see that installing new insulation can cause condensation formation within the enclosure assembly, and it can also cause freeze thaw cycles. Here's a screenshot of a typical WFI model. I know most of you are familiar with these, but for those who aren't, WFI is a one-dimensional hygrothermal analysis tool, which basically means it tracks how water vapor and heat flow through an assembly from one side to the other. In this assembly, you can see on the left, we have our exterior, and on the right is the interior. And each of these rectangles represents a material, and these materials have different hygrothermal properties. On the left, we have our marble, which we created by modifying a typical limestone material to contain marble material properties. And one key characteristic of marble is that it's pretty non-absorbent. If you think about it, if you have a big sheet of marble and you spray water at it, very little water will travel through it. But in reality, we don't often have a huge sheet of marble on the outside of buildings, but rather we have panels of marble with grouted joints. Because of that, we wanted to model the water penetration that occurs at those joints. So we set up this water source just inboard of the marble layer. These 6 layers here represent our 3 wides of brick. The reason there are 6 is that we split each of the wides into 2, so we can extract data about the outer and inner layers of each wide. We typically recommend that clients have us perform brick sampling. So we'll come to the site, take some samples, and then run lab tests on the brick to learn about what the brick's actual hygrothermal properties are. That's because all brick is different, depending on where it's from, how long it's been in use, different characteristics like that. But for this project, the client elected not to have us perform brick sampling. So we used our library of sample data that we have from other bricks and found some bricks with a similar construction time and a similar region as well, and estimate the properties of our brick layers. Lastly, I'll just mention this highly conductive airspace on the inboard side. This is the area where you'll see in a couple slides that the client was proposing adding spray foam and gypsum board. We wanted all of our WFI models to be the same width, so we would have consistent meshing across all of the models. And so we created these 2 highly conductive airspace layers. And this essentially conducts interior conditions to that inboard side of the existing gypsum plaster and lath, which is right here. These are the typical results from a WFI calculation. On the left in red, you can see our temperature graph. So this is a section cut, similar to what we've just been looking at. Left is exterior, right is interior. You can see the temperature fluctuates from about -25 up to about 30 degrees Celsius at the outboard side of the marble. But when we come to the interior, our temperature fluctuation is much less. The relative humidity, you can see here in green, it fluctuates highly right on the outboard layer of the marble, but not much is absorbed by the marble. The vast majority of our relative humidity kind of gets trapped around where that water source is between the marble and the brick layers, right here. We generally say that relative humidity that's above 95% would be cause for concern, and there's a risk of condensation in that layer. But the fact that condensation is occurring alone is not enough to say that this assembly is a bad assembly. In this case, we know that this assembly has been in the field performing for 120 years now. So it's working well. The humidity on that outboard layer of brick is not damaging to the brick. Also, brick isn't too sensitive to moisture, so we wouldn't expect it to be degrading or mold to be forming. And this is where the mold index would come in as well. If we had a material that was more sensitive to mold, we would be more concerned with that. Our total water content, you can see on the left graph at the bottom, it's very small. You can see the total water content in blue at the bottom. But here on the right, I also have kind of blown up the total water content over our simulation run, which in this case was a 10-year run. And you can see the total water content fluctuates each year. So over these 10 years, it gets wetter in the winter months, and then it kind of dries out over the summer and fall. And this is what we like to see in our results. We like to see the total water content is not increasing over time, but it's relatively stable. We expect that this assembly will continue to perform well. However, when we look at the results from our proposed assembly, we see that the total water content graph looks pretty different. So on the left is our proposed assembly. It's those same outboard layers, the same existing wall assembly, but then we have 3 inches of closed cell spray polyurethane foam and a 1/2 inch layer of interior gypsum board. One important thing to note about closed cell spray foam is that it acts as a vapor barrier. It doesn't allow vapor to pass through it. And I'll come back to why that's significant in a minute. On the right, you can see our total water content is increasing. We even extended the length of the simulation. So the last one we ran for 10 years, but this one we ran for 30 years. And over that entire 30-year period, the total water content continues to increase. You can see it fluctuates yearly, just like the other one, but the average is increasing over time and doesn't seem to be stabilizing. So what's going on here is that water and water vapor that are entering at the outboard side of the assembly are traveling through the brick as they were with the existing wall assembly, but then they aren't able to escape to the interior when they hit this vapor barrier, this layer of closed cell spray foam, which is acting as a vapor barrier. And therefore, that water gets trapped within this wall assembly and it has nowhere to go. So instead of using 3 inches of closed cell spray foam, we recommended using 3 inches of open cell spray foam and an inboard variable vapor retarder, and then the same interior chipboard. This open cell spray foam is not a vapor barrier. It allows vapor to pass through it and helps it not get trapped in those brick layers. And a variable vapor retarder is vapor tight when conditions are dry, like in the winter, but it also allows vapor to pass through when conditions are humid, so vapor doesn't build up in that assembly. You can see our total water content is a little bit greater in magnitude than for our baseline, but within about 1 or 2 years, we're stabilizing, and for the rest of the 30 run, being stable annual fluctuations. A quick note on the porosity of brick. If you put a brick into a bucket of water, it will absorb water, and that's called absorption. But if you leave a brick in a humid room, say 80% relative humidity, it will adsorb water from the air. And so it has these pores that are, if it's dry, the pores will be empty. And if you leave the brick in a humid room, then those pores will get full of water from the humidity in the air. And if you put that brick outside in the cold and it drops below freezing, all those tiny water droplets will freeze and expand. And we generally say that if more than 80% of the pores in the brick are full of water, so if it's over 80% saturated, then we would expect there to be damage if the brick were to freeze and then thaw. And that's what we refer to as freeze-thaw damage. For this project, that's where our main concern lay. You can see here in our baseline, we have saturation at all of the widths of brick that is below 2%. These bricks really are not getting wet at all. The bricks are freezing and thawing a lot, but that freeze-thaw cycle never occurs during a saturated period. So there's really no cause for concern with the existing assembly, which makes sense, again, because it's a historic building. We can look back on its history and see, okay, this wall assembly has been performing well. When we look at the proposed assembly, which has 3 inches of closed cell spray foam, you can see the maximum saturation gets up to about 11.6%. And in our recommended assembly, it's actually similar. The maximum saturation is about 11.7%. So if we just looked at these results, we would say there's probably no cause for concern because freeze-thaw cycles are occurring, but not when the saturation is over 80%. It's still below that critical saturation. However, when we look at our WFI results, the total water content, we see that in the proposed assembly, the total water content is continuing to increase. So the calculations we have are just for this 30-year period, but we would expect that saturation number to continue increasing over time and eventually cause freeze-thaw damage in the brick. On the other hand, our recommended assembly doesn't have that increase, so we expect that this saturation and around this number of freeze-thaw cycles is acceptable, and it won't change over time. Through all of this modeling, we saw that installing closed cell spray foam as proposed will likely trap moisture in the existing masonry, which could cause freeze-thaw cycles and related deterioration. Therefore, we recommended using open cell spray foam and a variable vapor retarder to address this issue. Quick little quiz question. Is it true or false that insulating an existing building can have both positive and negative effects? Give you some time to answer that.
Has that poll launched?
Don't think so. Let me try.
Oh.
It's good now?
Should be good now. Yep.
Okay. So go ahead and answer that. Can insulating an existing building have both positive and negative effects? All right. Correct. We've seen that. Oftentimes we only think that adding insulation can have positive effects that will help the building perform better and more energy efficiently. But we've also seen through this that it can actually have negative effects as well. Okay. Let's move on to our second case study, in which a client came to us proposing installing new windows on a historic masonry facade. This building was constructed in the 1930s. It's at a university in the Midwest. And when it was constructed, these windows were installed. So these windows are original to the building. They're single pane aluminum double hung windows. As you can imagine, windows from 1936 are not performing well today. They're beyond their service life. They've been having panes of glass fall out of these windows onto the sidewalk below. So as you can imagine, that's a pretty immediate life safety concern, which is why the university was trying to dig into this and trying to figure out what to do to either repair or replace these windows. This project was really interesting though, in that it wasn't just a straightforward decision about replacing. It was more of you had to consider all the different factors that were at play. For example, energy cost. So if we install new windows, will that help the building's energy performance and therefore help its economic performance, reduce the cost of energy? There's also an occupant comfort cost to be considered. The university had been hearing complaints of drafty windows and occupants were cold and uncomfortable. But then there's also the aesthetic side of things. There's a strong historic preservation community around this university that was pushing to leave the existing windows in place. Because it is true that no windows that are manufactured today will look exactly like these non-thermally broken windows from 1936. So they were pushing to just leave these windows in place. The university came to us asking us to perform energy modeling to determine what the energy cost impact would be of repairing or replacing these windows. That's because they wanted to have the data to come to the different stakeholders. So they have the sustainability group on campus, which is pushing to replace these windows and help make this building more energy efficient. But then on the other hand, they also have their historic preservation community, which is pushing not to touch the windows or to touch them as little as possible. So that's why the university asked us to perform energy modeling to determine the energy cost impact of repairing or replacing these windows. You can see here are 3 different window assemblies that we modeled. We set up 3 energy models, one for each of these options. The first option is leaving the existing windows in place, and this one assumes that the perimeter seals would be repaired, and also that they would, I believe, perform annual assessments of the building just to make sure that there are no loose panes of glass about to fall out, and they would repair windows where that was happening. So it does still address the life safety concern, but it doesn't really address our other concerns. Our remediation option is doing those same repairs to the existing windows, but then also adding an interior storm window, which is right here. And this would help reduce the air leakiness and ideally help make the occupants more comfortable. The third option was fully replacing the windows. You can see this is a much more modern looking window sill detail. We have an insulating glass unit, which is 2 panes of glass here with an air space in between. And you'll also notice that this one looks a lot bulkier. If you're standing on the outside here, you'll see this distance, which is called the sight line, from the base of the glass until the base of the rough opening, is a lot taller. It's a lot thicker frame than the existing windows. So it would be a pretty drastic change to the aesthetics of the building. We used therm and window to calculate the overall U factor, solar heat gain coefficient, and visible light transmittance for these 3 options. We calculated separate U factors for the frame and perimeter, edge of glass, and center of glass. And you'll also notice that all of our models included 1 foot of perimeter area. So that's to capture the thermal bridging effects that happen, for example, below the sill within the first foot of wall, and similarly at the jamb head. So in our energy model, when we set up the windows, we set them up to be a little bit bigger than the existing windows. And then we entered in the overall combined U factor, solar heat gain coefficient, and visible light transmittance for that whole window plus 1 foot perimeter area. So among our 3 models, we varied the thermal performance, and we also varied the air infiltration rates. In the existing windows, we performed field testing to determine what their air infiltration rate was, and we found that it was 1.8 cubic feet per minute per square foot when tested at 75 pascals. And for those who are familiar with the energy code, that's a very leaky window. ASHRAE 90.1's maximum allowable air leakage rate is only 0.2 CFM per square foot. So the existing windows are 9 times air leakier than code. So we assumed that the replacement windows would reach that air leakage rate of code. We left the existing windows as our 1.8 CFM per square foot, and we assumed the storm window would be in between those 2, kind of based on some product testing and based on the air infiltration rate of the existing windows. Our 3 energy models all had identical opaque assemblies. You can see here sections through the above grade wall and through the roof. Our above grade walls are limestone over concrete and then various interior finishes. And our roof is a cast in place concrete slab with 2 inches of insulation and then roofing fill and some tiles on top. One important thing to note here is that there's no insulation in the walls, which is not uncommon for this period. But as you can imagine, there's a lot of heat loss going on through the walls in this building. And this will come back later. It's important to note that a lot of heat loss is happening at the walls, and also the majority of this building envelope area is opaque walls. There are very few windows and they're very small. They're actually only about 4% of the overall envelope area. So we kind of knew going into this that any changes to the window assemblies would not have a drastic overall effect on overall energy performance. Another interesting thing to note with these 3 details is that's kind of unique for historic building work is that they're very messy. You can see here on the roof detail, you can almost read, it says 2 inches of insulation, but typically the drawings that we work with for historic buildings are also historic. So they were drawn, 100 years ago, and they were scanned in at some point, usually. So it's a lot of digging and a lot of asking different people and trying to find the drawings that you need in the archives. And that kind of adds to the time intensity of a project like this. It's just digging up those answers. We used Design Builder, which is a graphical user interface that runs on Energy Plus. And you can see here a screenshot of our model and also a photo of the building itself. See how small those windows are? It's a very small window area. As I mentioned, only 4% window to wall ratio. In Design Builder, you enter inputs like the geometry, which I've talked about, the enclosure systems, the opaque and glazing systems. You also have to enter occupancy types and patterns. So for that, we worked with the client to determine when this building was occupied and by how many people. And we also modeled HVAC equipment, which was another interesting scavenger hunt, trying to figure out how this building's HVAC was designed. There were several renovation projects for the HVAC over the decades. So we did a lot of tracking down to try to model the HVAC systems accurately in Design Builder. And you can also model water usage and lighting, but for this project, those would remain the same across all 3 models. So we elected not to model them. And one important thing to note with this is that we're not trying to calculate the actual energy use of the building in this case. Rather, we're trying to calculate the difference in the energy savings among our 3 options. So we modeled the HVAC and the occupancy as accurately as possible, but we need to remember that this is not going to give them their actual energy costs of the existing building. The university asked us to provide them with an estimated payback time for each of the options. So you can see on the left that we do have a little bit of cost savings annually, but it's very small. And the cost of the windows themselves are very high. And so therefore, our estimated payback time is in the hundreds of years. Basically, this project, whichever option we go with, is not going to pay for itself within the life of the window products. And this comes back to our window to wall ratio and the fact that such a small percentage of this building was windows. So even if you made those windows the most thermally efficient windows on the planet, you still wouldn't have a drastic effect on the overall energy performance of the building. As I mentioned, this project also had a lot of other factors at play. We did do some occupant interviews and learned about their comfort concerns. There are drafty windows. The meeting rail is not sealed. You can see that there are deteriorated seals and gaskets, and also some of the windows are inoperable. There are also aesthetic concerns, which I mentioned that the historic preservation community has. It's not a landmarked building, but it is historic and it's iconic in this local community. Replacing the windows would cause there to be increased sight lines, and changing single pane glass to an insulating glass unit would have an impact on how the windows appear and reflectivity, things like that. And I'll actually get into that a little more on another case study. So we came to our client with the result that the energy cost is not significantly affected by window remediation or replacement. However, we still recommended replacing the windows to address the life safety, occupant comfort, and water penetration concerns. And in the long run, that will probably give them the best performance. And at the end of the day, the client did decide to replace, but they felt comfortable using aesthetics and as the main driver for their window selection. So when they're looking at all the different window products out there, they can be very careful to look for one that is a good historic replica window and not be as focused on finding the most energy efficient window out there. Okay, this is a more subjective question. In a project like this, which of these factors do you think is the most important? I took out life safety because I think most of us think life safety is pretty important, but after that, which of these is most important?
Abigail, you might have to launch the poll. Yeah.
Sure. There we go. Okay. Which of these is most important to you? All right, that's interesting. Yeah, occupant comfort cost is definitely critical. I'm surprised though that our group is a little bit different than the main players in this project. And I do see your questions coming in, but we'll talk through all of those at the end. Great questions, keep them coming. Okay, our third case study is one in which a client was proposing installing new historic replica bronze doors. This building was constructed in 1971, so it's not as historic as the previous ones, but it still has a lot of unique issues and was built in a different era of construction almost. The existing doors are non-thermally broken and they're original to the building. This is up at a balcony level and there's this big wall of curtain wall here. You can see in this rendering. The curtain wall was replaced in 1987, but at that time, these doors were removed and reinstalled. So they're the same as the original doors. This is a museum space and these doors have been exhibiting condensation on the interior. And the reason that those are related is that oftentimes museum spaces are highly conditioned. They're usually more humid than like an office or a residential space, usually to keep different artifacts or pieces of art at a specific set point. And so often we do see condensation formation in museum spaces. The proposal was to replace these doors with historic replica, but thermally broken bronze doors. And we wanted to see, would this help address the condensation issue? Okay, when we install new doors, we see that this can affect condensation formation on those doors. To start this project, we set up some data loggers at the glass on the inside and outside of the glass at two different locations. You can see here there's a direct correlation between the interior temperature and the exterior temperature, which makes sense. But an important thing to note is that our interior set point is 70 degrees Fahrenheit, but almost none of these interior temperatures are at or above 70 degrees. They're all in the range of 62 to 67 degrees Fahrenheit. And this is common. We see our near glass temperatures are usually not at the interior set points. But this is an important thing to note for modeling because we can't always assume that the set point is what the actual interior temp and RH are at the window location. So we need to keep those things in mind. This is a detail at the head of the door. We did modeling at the head and jambs and sill, but for this presentation, I'll just be showing the head at all of the different iterations we did. You can see here's our door head. This is the existing door, non-thermally broken. Up here we have our new curtain wall system. On the left is the exterior, which we varied the temperature to try to figure out condensation when condensation would form. And on the right, we also varied the interior because, as I said, we can't assume that it's 70 degrees Fahrenheit and 50% RH. I've traced out here in black the isotherm at the dew point. And an isotherm is a line that connects all the points of equal temperature. And in this case, I have highlighted it at the dew point, which is based on the assumed interior temp and RH for this model. When the dew point temperature, when the isotherm reaches the interior here, that means that all of these temperatures are lower than the dew point. And I've highlighted that in red. That's where we would expect condensation to form. So if the temperatures on an interior surface are below the dew point, we generally say there's the potential for condensation. Okay, here are our models of the thermally broken door. You can see it's a little bit different profile with and without heat trace. So we started by modeling it without heat trace, but we saw that we were still getting some below dew point temperatures at interior surfaces. Not nearly as bad as before, but we're still seeing that condensation is likely to occur. Therefore, we modeled some heat trace around the door perimeter, and we're kind of able to push the dew point isotherm towards the exterior and give us a much greater certainty that we would avoid condensation over time. This is to give you an idea of where the heat trace would be at the head and jambs, and just a side note that it's important to check with local electrical codes when you're doing this kind of work. From all of these models, we saw that condensation will still likely occur, but in different numbers of hours per year with and without heat trace. For example, when we have our new thermally broken door without heat trace here, if we look at just the head, we see that condensation formation is expected to start occurring when the exterior temperature drops below 29 degrees Fahrenheit. And in Washington, DC, where this project was, the temperature is below 29 degrees Fahrenheit for about 400 hours each year. So basically, when the temperature is below 29, we expect that dew point isotherm to reach the interior surface and there to be condensation. Without, we have an expectation for condensation for a significant number of hours each year, especially at the jambs. But when we add the heat trace, we reduce that to almost zero. And this is kind of a question that comes back to the client and the architect about whether condensation is acceptable at this location, whether it will damage interior finishes, or whether it's okay if it's just condensing and then drying out. But this is what we found from our thermal modeling, and we were able to present both options. Through this project, we saw that new thermal breaks alone were not sufficient to address condensation, but adding heat does drastically reduce condensation hours. Here's a quick quiz question. Why is the dew point relevant in thermal modeling? Okay, I launched that, so go ahead and take a look when you're reading these options. I'll give us another 5 seconds or so. All right, great. Yes, it is B. They're important because interior surface temperatures below the dew point can cause condensation. Okay, let's move on to our fourth case study, in which a client was trying to explore different glass types for use at new windows. This project is located in Boston. It's at a historic church that was constructed around 1905. In the photo on the left, you can see the portico area. On the left, we have our exterior doors. They're these beautiful historic wood doors. And on the right, we currently have these archways. This building has been under renovation for 5 or 10 years at this point. But the next stage of the renovation includes adding new curtain wall system and new glass doors underneath these archways. So you can see here a section cut through the head of the proposed curtain wall system. The existing assembly is all grayed out, and we have this note, which is pretty common on historic renovation projects, to take care not to damage the existing construction. We also have our continuous steel plate here supporting the curtain wall, but it's not anchored back to the existing limestone or any of the existing materials. And we try not to bear loads on existing structures. When we look at our matrix, we see that installing new windows and doors can cause condensation. Here's just a plan of the vestibule to give you an idea of what we're working with. I've highlighted the vestibule area in blue, and in yellow, we have our proposed glass curtain wall system in those archways that we were just looking at in the picture. And we can also see the proposed heaters at the base of the wall. And the existing wood doors are located right here. Okay, the main question for this project was whether to use monolithic glass or an insulating glass unit. So our role was to figure out what the condensation risk would be for each of these options. On the left, you can see our therm model for monolithic glass. It's just a single pane of glass. And on the right, you can see it for an IGU. And that IGU has 2 panes of glass and a layer of air and argon in between. For both cases, we assumed interior conditions of 69 degrees Fahrenheit and exterior conditions at the ASHRAE 99.6 heating design dry bulb temp for Boston, which is 8.1 degrees Fahrenheit. When we look at the temperature outputs from therm, we see that the coldest surface temperature for the monolithic glass occurs all the way down here on the interior surface of the glass. But this whole glass area is in this purplish range, which if we look at our key, we see that temperatures there are about 5 to 10 degrees Fahrenheit, very cold. With the insulating glass unit, our lowest surface temp actually occurs back here. There's a little void inside the assembly here. But when we look at insulating glass unit, we see that the inboard surface is all in this red to orange range. So those temperatures look to be about 50 degrees Fahrenheit. Again, I've traced the isotherm lines just to show where our dew point occurs. In this case, we're assuming interior conditions of 69 degrees Fahrenheit and 45% RH. And that's pretty high humidity for a typical church, but this church has an organ inside, and so it needs to be kept pretty humid. And so we assume that some of that humidity will also condition this vestibule space. In the monolithic glass therm model, we see that there's a significant amount of condensation and below dew point temperatures at the interior surface. But in the insulating glass unit, that isotherm, our dew point isotherm, turns down and runs parallel to the plane of glass and never actually touches the interior surface. So we wouldn't expect there to be condensation with an insulating glass unit. This project also had some important aesthetic considerations, especially from the architect's point of view. Monolithic glass and insulating glass units look different. With an IGU, you can often see the spacer bar, like right here, you can see this usually stainless steel spacer bar, it kind of stands out. And the reflectivity works a little bit differently with monolithic glass versus when you have 2 or 3 layers of glass. And in this project, the architect was very set on using monolithic glass because of how it looked. They wanted that very sleek look. And so they were definitely leaning towards monolithic glass from the beginning. One important thing to note is that in this application, since the glass curtain wall does go all the way down to the ground, you're going to need to explore safety glazing options and using laminates and different interlayers to create safety glazing in that area, or potentially tempered glass. So as we saw for our therm models, using monolithic glass will likely lead to condensation on the interior surface of the glass. And therefore, we recommend we recommended using an IGU instead of monolithic glass. I think anybody could look at those therm models and see the IGU is the preferable option. However, the architect is, in spite of all this, still deciding to use monolithic glass. And so now we're at the point in design where we're trying to help them figure out how to mitigate this expected condensation on the inboard side of that monolithic glass. For example, with a warm air wash at the ceiling. Okay, one last poll question. I'm curious if you prefer the look of monolithic glass or an insulating glass unit. They do look a little bit differently, but I'm curious what your preferences are just based on aesthetics alone. Interesting. Give you 5 more seconds. Okay, so we have a lot of people with no opinion. That's a good point. I wish we could show the architect this because it doesn't matter too much. Okay, let's move on to our conclusions. So from each of these case studies, we've learned about the importance of using the correct modeling software to evaluate different risks. In our first case study, where they were proposing installing insulation on the inboard side of a multi-wide masonry wall, we used hygrothermal modeling to assess the risk of freeze-thaw cycles and the associated masonry deterioration. In our second case study, in which a client was proposing remediating or replacing existing historic windows, we used whole building energy modeling and associated thermal modeling to evaluate window replacement options. In our third case study, in which a client wanted to replace some historic bronze doors with historic replica thermally broken bronze doors, we used thermal modeling to assess condensation risk with thermal breaks and also with heat trace. In our fourth case study, we evaluated the use of monolithic glass versus an IGU and used thermal modeling to evaluate those two options. Through all of these, we've seen that historic building renovations do present unique challenges. We often have a lot of questions about what's there in the field. We might have to do exploratory openings. We might have to do digging to figure out what the assemblies are made of. It's usually a lot less straightforward than a new design project because you don't know exactly what you're working with. There are many softwares out there that are available for us to use to evaluate different interventions, but those softwares are only as useful as our understanding of the potential issues. And with that, I will leave my email up on the screen for a minute, and then we can get started with questions.
Perfect. Thanks, Abigail. I hope, yeah, people can hear me.
Yep.
Thanks, Abigail. That was an excellent presentation. I particularly like that last sentence. The software is only as useful as the questions we're trying to answer. That's great for this community. I feel like a lot of people will agree with you there. We do have a couple of questions.
Great.
I'm going to, I had questions too, but I'm going to let the guests ask some. So first is from Rajiv. He asks, at what stages of a building renovation or retrofit project are simulation studies more prominently consulted? Is it just during the early stage or even later down the project timeline?
Yeah, this is a really, really good question. There are a lot of answers. Typically, if we're doing a historic renovation like I've been talking about today, we want to be consulted early on to try to figure out, like before it's too late, if this is actually a good design strategy. But I've also been on projects, especially new design projects, where like throughout the construction process, there will be changes and the contractor will come to us and say, can we make this change at this soffit condition? And so we'll use building, we'll run a WFI model or something to try to figure out if that change would be acceptable or if it would be harmful. So I think really at all stages of the design process, it can be used.
Thanks. Thanks, Abigail. So there was a question asking if this would be available. This recording would be available online. Yes, it's also on our YouTube channel. So if you'd like, please consider subscribing to our YouTube channel, IBIPSA USA, and we'll have this recording there as well. Our second question was from Patrick Keeney. He actually had his hand raised. So I'm gonna let him ask him to unmute myself or unmute himself, and he can ask the question.
Hey, can you guys hear me?
Yep.
Yeah, hey, thanks, Gokul. Hey, Abigail. So yeah, I just had a question. I think it was on your second example. You mentioned that the frame effect for that small window, and then you wrapped the frame effect around, I guess it was like the stone outside, and then in the energy model, you enlarged the windows to account for that. That all makes sense from a U value standpoint. I'm curious how you tackled that from like a solar heat gain standpoint. If you just made the frames around the edge really large, because if you made the window itself larger, wouldn't you get more solar heat gain through vision glass? Thank you.
Yeah, thanks for the question. I believe what we did, this project was a couple of years ago, but I believe what we did was do a similar, like an area weighted average, and assumed, well, no, because your solar heat gain coefficient is going to be 0. I would have to look into that and like dig into that project more. But if you're curious, if you could email me, I'd love to give you a little more information.
Alrighty, no worries. Thanks, Abigail.
And maybe CC me in that email as well, because I'd like to know more too. We have 5 minutes, and before I ask more questions, I do want to, I had a couple more announcements, sorry. So this is the IBIPSA USA Research Committee webinar. If you enjoyed this webinar, do consider joining us at the IBIPSA USA Research Committee. Email research@ibipsa.us or visit the link in the Zoom chat I'm going to paste for more information. If you're watching us on YouTube, please like the video and consider subscribing to our YouTube channel. So those are a couple of announcements. We can get back to questions. So Abigail, I had a question of my own too. So I believe it was your second example, which had the 4% window wall ratio, correct? So how did I was quite surprised that the clients, it looked like all the paybacks were really, really long and things were expensive. And I wanted to understand, so how did the conversation with the clients go? Why were it looks like they did end up replacing it. So I was quite surprised that that happened. So what was it just the safety reason then, or why were they keen on replacing it?
Yeah, so the safety reason was a big factor, but I think the main reason that they wanted us to do energy modeling was so that they would have some numbers to back them up with when they were coming to all these different stakeholders. So even though those numbers, they didn't show much energy savings, they were able to show something and be able to use that in that whole discussion. And also another part of that project is that the university was interested in having us do these types of energy models for some different buildings on campus. So this was kind of the first one that they wanted to give us a try and like see how useful the energy modeling would be and what that process would look like.
That's great. I think it's also great that the university values energy modeling beyond just monetary gains. And for my, I see some questions. Oh, this is from Ling Ling. She asks, can secondary single glazing addition be considered for historical buildings rather than replacing with double glazing panels?
Is that like referring to storm windows, like a second secondary single glazing, like a second window
Yeah,
altogether.
Ling Ling, if you are with us, I'm gonna let you unmute yourself and you could ask the question directly.
Hello.
Yep, we
Hi.
can hear you.
Yeah, I'm calling from UK. Quite normally the historical building here, not really consider any replacing of the I think you call it IP independent glazing, the double glazing that you were showing, and they quite
Yeah.
often it was either just staying with the original one or adding another type of high performance single glazing that doesn't extrude or change the look. In the UK, is it a more common practice on this? I believe this will still have the problem with condensation from the inside, but I think the conservation ideas is probably stronger here, that we don't really consider replacing. I mean, that's, you've got listed building or conservation area which you are not allowed to change any of the look whatsoever. So if there's a regulation so in place in US, and how do you deal with there's no changing is available, and just see how US is dealing with this type of situation with more restrictions. Sorry. Thank you.
Yes, thanks for the question. This building that I talked about in this presentation is not listed on a historic registry or anything, and I think that that's why we were able to just move forward with the replacement. I'm trying to think if I don't think I've personally ever done a model that was for a landmarked building or anything, but I can imagine that in those cases it would be harder, if not impossible, to replace the existing windows, because that would, as you said, have a big impact on the overall aesthetics of the building. We have done a lot of modeling with storm windows on the interior, and I have seen them go in on some windows, so those don't change the appearance and do help with the performance, like you mentioned. But there are also a lot of other things to consider, like thermal stresses from if you build up a lot of heat in that cavity, things like that. So they come with their own unique set of challenges too.
Thank you.
Thanks, Ling Ling, for the question, and thanks once again, Abigail, for answering it. I have, so we are at the top of the hour. I have a couple more questions for Abigail, but I want to let the others know that they're free to drop off if they want to. And the absence of more questions, I'm going to ask mine. So Abigail, if you, so my first question, if you could share your presentation to your, I believe it was your third example where you showed the heat trace line. And this question is coming from a place of ignorance, and I'm going to go by the no stupid questions rule. So could you explain what heat trace is for someone who's not familiar with it?
Yeah, so there are different things we can do to heat the inboard surfaces. Sometimes we'll have a warm air wash, which I mentioned before, which is just like squirting warm air near the windows to kind of dry them off, basically. In this case, I didn't get into the electrical design. We don't really do that at SGH, but it's basically a wire with a current that's running through it. And so it's warm. And you sometimes see this like at roof edges where we're worried about snow and ice building up and falling on people. We'll put heat trace along the outside, or at freezing sprinkler heads is another project I'm working on. But basically you're just running electricity through these wires all the time, or not all the time, depending on, seasonally when it's required. And that heats up the surrounding surfaces. Got it.
And I assume it's a common practice here in the United States. Is that true?
It's relatively common when it comes to historic buildings. We typically try not to do it on new build. It's not like you wouldn't want to design something that's built with heat trace in it. But
Mhm.
when you already have a lot of constraints and there is not much else you can do, it's kind of a last resort of ways to help and to make things better.
So we have an anonymous question. They asked, is it visible or is it inside the mullion? I believe they're asking about the heat trace.
Just based on these details, it looks like it would be, you could see this probably metal rectangular box running up the jambs at the head, but you wouldn't actually see the wires. I mean, when it's on roofs, you can't actually see the wires.
Nice. And my absolute last question. So this is more understanding envelope or modeling, thermal modeling in general. Do you see a lot of clients just wanting this kind of consulting just on its own, and do you see are you seeing value with respect to your clients, or do they want it as part of a bigger package, or what's the conversation like?
I think that we generally try to incorporate it into a bigger package. So if we're doing English consulting and we see there's going to be a detail that has a risk of one of these issues, we would recommend running different models for it. Occasionally, we do have clients come to us with a problem and ask us to model it, but I think it's more in the case of trying to design for it ahead of time and trying to avoid these problems in the first place.
That's great. Yeah, that's good to know too, that these exist and these are being done. All right, I'm gonna stop the recording. So those of us that are joining us on YouTube and Zoom, thank you for joining us. This was a great presentation, Abigail. I felt like it was really well presented. I learned a lot. It was in that mix between talking to the experts and also letting novice people learn about the project. So thank you once again. We'll let you know what the numbers for the viewing are 2 weeks after. But yeah, thanks for joining us.
Yeah, thanks for having me. I appreciate it.